Hey, hello everyone, and welcome to the session. If you want the link for yesterday's session, let me click on that and keep it handy. And we are also going to have thumbnails for this, and we will ensure that we have thumbnails. Okay, once again. Okay, so how many people do we have? 654 people registered out of that 14 are live. I think we should get started. So we got started with NLP and we covered a lot of ground with respect to natural language processing. Let me open the mind map and oops, not this one. Let me open the right mind map and then we shall proceed further by doing a quick recap. Okay, so we have text mining NLP here. We have started off by discussing about text mining, which deals with unstructured textual data. We have also discussed about NLP, natural language processing, wherein we discussed about unstructured data, which is textual in format and also audio and speech. We have also discussed about two categories, which is NLU and NLG. And then we discussed about a lot of pre-processing techniques. And then we have POS, parts of speech. So here we have tokenization, regular expressions, text blob, keras, types of tokenizers, parts of speech tagging, stop word removal, text normalization, spelling correction, stemming, lemmatization, right? Named entity recognition, word sense disambiguation. Then we have sentence boundary detection, a lot of things. Okay, and today we are going to take this discussion further and discuss about something called as topic discovery and modeling. When it comes to topic discovery and modeling, there are primarily two things. One is called as LSA, which is also called as LSI, and then we have LDA. We're going to discuss about these two, and then of course there are a few more other things that we will have to discuss. So we covered a lot of ground in terms of discussing about all of these various techniques, and then now we are in terms of scraping the web and then discovery, topic discovery, LSA. LSA stands for Latent Semantic Analysis, which is also called as LSI, Latent Semantic Indexing, which was invented in 1980 to index the various documents. It is heavily used in search engine optimization. There is also something else which is called as coherence model, which is used to measure the accuracy of your LSA or LSI models. GenSim library, which is part of Python, has two classes. One is called as LDA model, another is called as LSI model. These classes can be used to handle LDA or LSI. Then you have terms to topics matrix, topic importance matrix, and topics to document matrix. What are these three? Simple. Whenever unstructured textual data is provided to you, that would be in unstructured format. How do you convert that to a structured format? While there are many ways, one way to convert the data to a structured format is to have a document term matrix. Okay, it is all about to have document term matrix. And this document term matrix will be very large. It will be extremely large. Since this is going to be extremely large, we will have to decompose that into smaller components. And in order to decompose these into smaller components, we use singular value decomposition. What singular value decomposition does is, it will take your document term matrix and it is going to decompose this into U sigma V transpose. This component that you're seeing, terms to topics, is called as U. The topic importance is given using sigma. Topics to document is given using V transpose. U sigma V transpose. So from unstructured data, when you convert your data to structured format, you resort to document term matrix or a term document matrix. Means if it's term document matrix, how would it look like? Terms will be on x-axis, documents will be on columns, not x-axis, rows and columns. Sorry, let me take back that word. Yeah, terms will be on rows, documents will be on columns. So in order to understand this, we have also looked at SVD. Where is SVD? Here. We understood this concept of how we decompose the data, so on and so forth. Okay, all these things we discussed. If you remember, Lena, good enough. That means you understood SVD. Yeah, all right. So even before we proceed further, I want to give you a brief introduction about matrix operations. Let me use this, and then let me draw. Let me give you a few matrix operations. If I take 1, 2, and if I take a transpose of that, what do you get? 1, 2. If you take 1, 2, 3, and 4, and when you take a transpose of that, rows become columns. Rows become columns. If you have 1, 2, 3, 4, 5, 6, and then if you take a transpose of that, you get 1, 2, 3, 4, 5, 6. So rows will become columns. Simple. Rows will become columns. This is a simple matrix transpose. This, I think you would say that, oh, this is a kid's play, child's play. Why are you explaining these things? Hold on. We will now graduate slowly. We will move from one class to another. Say you have matrix multiplication. If you have a matrix A, which is of dimension 3 by 4, And if you want to say multiply it with another matrix whose dimension is 4 by 5, can you multiply? Oh yes, absolutely you can. How do you know that? If the number of columns and the number of rows here are the same, then you get a matrix AB 3 by 5. If you have a matrix, but if I take B, which is 4 by 5, if I were to multiply it with A, which is 3 by 4, can we multiply? No, we cannot. Why? Because here and here you have different numbers. So the number of columns here do not match with the number of rows. Hence, matrix multiplication is not possible. Okay, this is also clear for you all. So let's move on to the next thing, which is if at all you have two matrices A multiplied by B, if it is going to give you identity matrix. What is an identity matrix? You'll have one along the diagonal, and along the off diagonal you'll have zeros. If you have such a representation, then B is equal to A inverse. A, B is right inverse of A. B is right inverse of A, because A into B is not equivalent to B into A. If I say B into A is equal to identity, you cannot say, okay, A into B is identity, this is this, so these two are the same. We cannot say that, because A multiplied by B might be different to B multiplied by A. Okay, hence you say right inverse, left inverse in that way. All right, this is also clear. Next, let me explain about orthogonal matrix. Orthogonal matrix. All these are important because when you work on dimension reduction techniques such as principal component analysis or singular value decomposition, then you need to understand the matrix operations. And if you understand all these matrix operations and SVD, only then you will understand LSA, which is also called as LSI. Okay, don't think that we are discussing all these things for fun. No. Okay, say you have a matrix wherein you have 2 by 3, 1 by 3, 2 by 3. I'm just taking some numbers because these numbers give you a perfect way to explain basically. So if you have minus 2 by 3, 2 by 3, 1 by 3, and if you have say 1 by 3, 2 by 3, okay, here you'll have minus 2 by 3. Okay, so if you have a matrix like this matrix is called as orthogonal matrix. Okay, then if this is A into A transpose will be equivalent to identity matrix. How? Okay, first of all, what is orthogonal? Orthogonal means if you find out the sum product of any two columns, column 1 and 2 or 2 and 3 or 1 and 3, any two columns, sum product will be equivalent to 0. So you multiply these two. If you multiply these two, you get minus 4 by 9. And then when you take a product of these two, you get 2 by 9. And then when you multiply these two, you get 2 by 9. When you add these, you get 0. Those are these diagonal off diagonal elements, zeros. Any two columns, take any two columns and multiply, you get zeros. And then if you take a single column, if you square and sum them, it should be equivalent to 1. These are the properties of orthogonal matrix. So if you take all these values, so 2 by 3 whole square plus 1 by 3 whole square plus 2 by 3 whole square, how would you write that? 4 by 9 plus 1 by 9 plus 4 by 9. When you add these, you get 9 by 9, and then these two get cancelled out, you get 1. Take any column, square it and add it, you get 1. So that means you will have unit vector. Okay, and sum product of any two columns will be equal to 0. If you have these two properties, it is called as orthogonal matrix. And the next thing is eigenvectors and eigenvalues. If you have a matrix A, and then if you take a vector V, it is equal to lambda into vector V. So if V is eigenvector, I mean in this kind of a setup, V is called as eigenvector and lambda is called as eigenvalue. Hey friends, at this point of time, we are discussing about alphabets, assume A, B, C, D. You don't ask your teacher on why are we learning these things. Why do you learn alphabets? To form words. To form words, you'll have to graduate or you have to move to the next class, right? So that is exactly what we are doing at this point of time. We are just discussing about basic matrix operations. Hey, why do you need this? Is like asking a question on why do you need to learn alphabets? You learn alphabets in English to move to the next class and learn about words. So basic matrix operations help you in understanding various concepts, including your dimension reduction techniques such as PCA and SPD. Now you don't go and ask your teacher on, hey, why am I learning A for apple? Why do I need to learn apple, ball? Because you need to form sentences when you move to the next class, right? In that way, why is this needed? To understand latent semantic analysis, which is also called as LSI. We are traversing this path and hence we are understanding this. And why do you need LSA and LSI? For performing topic modeling. And what is this topic modeling? It is one of the concepts of NLP. And why do you need NLP? To extract meaningful insights. So to draw insights from textual data. Of course, textual data is unstructured in format. You need to do something, right? If customer says, hey, here is my data, you cannot say, oh, I cannot, please tell me what should I do with this. Come on, you have to get started as data scientists or AI experts, and you should start drawing the insights. Okay, so hope this is setting the big context, big picture. Understand the ABCDs, then learn the words, then learn the sentences, then form the paragraphs, then probably you graduate, okay, in that way. So we are now at this point of time understanding just basic basic matrix operations. Where is it used? Why is it used? How is it used? Hold on. First, understand the concept. After you understand this concept, I'm telling you that it can be implemented here in SVD and also PCA. And I'm also saying that these kind of concepts, if you understand, it makes your life easier to understand the other advanced concepts. Eigenvector, eigenvalues will come in network analytics. Yep. And it will come in various other places. Then you shouldn't be surprised on what is this, right? This is just a property of a vector, eigenvector. Anyways, now let's get back to our discussion. So to understand eigenvector and eigenvalue, let me take a quick example wherein I'm going to just take a few values here like this. Say this is a matrix that we have. Now, if this A is a matrix, can I have this kind of an equation wherein if I multiply this matrix with a vector, I get a value multiplied by the same vector. If I take a matrix and multiply by a vector, would I get some value multiplied by vector, and will those two be the same? Let's understand. So if this is your matrix 2, 0, 0 and 0.5, and if you multiply this with say a vector which is 1, 0, so here also I'll put 1, 0 because I need the same vector on both sides. And lambda, I'll just simply take 2. You multiply and see it'll be the same. Okay, 2 into 1 plus 0 into 0 will be 2. 0 into this plus 0.5 into this also will be 0. So you'll still get 1, 2, 0. Here also, if you multiply 2 with this, you get 2. 2 with this, you'll get 0. So these two are equal. So your algorithm behind the scenes, when you use code program, it will just look at various combination of values which are making the right hand side and the left hand side equal. That's it. Now let's understand this concept using a geometrical representation. If I say 1, 0, this is obviously 0, right? 1, 0 means 1 on x-axis, 0 on y-axis. So 1, this is 0. 1, 0 is this point. This is your vector. If I multiply this with 2, you'll get 2 and 0, right? You get this when you multiply this. 2, 0 means 2 would be here. 0 is the same thing. So you get 2, 0. And here you have another vector. So you have a vector 1, 0. You have another vector 2, 0. Okay. Now what has happened here is direction remains the same. The direction here is the same. The only thing is the magnitude changed, but the direction didn't change. Okay, remember that one thing. So when you multiply a vector with a value, the vector direction didn't change. First thing. Second, eigenvectors and eigenvectors and eigenvalues can be different values. So that means you can have different solutions. So if I take the same setting wherein you have 2, 0, 0.5, different set of values also can form the same kind of expression as this. That means if you take 0, 1, which is equal to 0.5 into 0, 1. When you do this 0 and 1 that you have here can be written in this way. 0 and 1. And then this is your vector. If you multiply um, by 0.5, what do you get? 0, and here you'll get 0.5. That means x is 0, y is 0.5. Where would that be? It would be here, 0.5. So this point would be 0, 0.5. 0, 0.5. Okay, here, this is the direction. So the direction still remains the same, but the magnitude changed. Those vectors which do not change the direction is called as eigenvector. Okay. So eigenvectors are those which do not change the direction. Now I can give you a different example also, wherein let me erase these things. Let me take a different example altogether. If I take a value such as 1, 1. If you use a vector 1, 1, what do you get? 2 into 1 plus 0 into 1 will be 2. 0 into 1 is 0. 0.5 into 1 will be 0.5. So these two vectors would be very different, isn't it? So let's try out. 1, 1 would be 1 on x-axis, 1 on y-axis, this point. So the direction will be like this. 2, 0.5. 2 would be here. 0.5 would be somewhere here, this point. So it'll be like this. So the directions are different. So this is not an eigenvector. Okay, this is not an eigenvector because when you use eigenvectors, directions do not change. This is one important property that you need to remember to be able to understand SVD, to be able to understand principal component analysis, to be able to understand a lot of concepts which are going to come your way. Okay, so just bear that in mind. And this is basic matrix operation, which is very, very important for you to proceed further. Next thing is, we need to understand SVD. SVD is nothing but you take a matrix and decompose it into U, sigma, V transpose. Why do you do that? Is something that we have discussed yesterday to compress. I mean, instead of taking the complete data, complete matrix, you just use one row, one diagonal element, one column, one diagonal element, and one row. Two columns, two diagonal elements, and two rows, something on those lines, and solve it. It'll be faster. That's the reason. Not just that, there's also some other logic associated with that, and that logic we will understand when we discuss about LSI, right? Or LSA, both mean the same. These techniques are unsupervised learning techniques, right? And you already know that when it comes to data mining, you'll have two branches, supervised and unsupervised. In supervised learning, the output variable y is known, and in unsupervised learning, output variable y is unknown. And this is unsupervised learning, LSA or LSI. And we are now discussing about topic modeling. Okay. So this is the SVD formation that we will look at. This is a matrix. We will decompose this into U. sigma V transpose. So you know about matrix multiplications and all that. Wonderful, right? So, where are we now? Yep, here. If at all, there are 5 documents. Document could be a single sentence. Document could be an entire paragraph. Document could be an entire page. Document could be a single word. Document could be a single alphabet. Depends. It could be a movie review. One entire movie review could be one document. One entire review written on Amazon could be one document. Okay, or any survey that you conduct, survey responses. Each survey response could be one document. It depends on what you are trying to analyze. So once, say you have 5 documents which are available. Document 1 says Romeo and Juliet. Document 2 says Juliet. Oh, happy dagger. And then document 3, Romeo died by dagger. Document 4, live free or die. That's the New Hampshire's motto. Document 5, did you know New Hampshire is in England? You have 5 documents. And someone is searching on Google, for example, they go and search as dice dagger. Then, which of these documents should be extracted? Which of these documents should be extracted from the uh, pool of documents and then displayed to you? If that's the question, then you might want to extract document 3 first. Why is that so? Because that has both die and dagger. Both of those exist. Great. So document 3 would come out. Then which document? Probably this document because it has dagger. So then you'll have document 2. Then maybe document 4 because it has the word die. And document 5 and 1 do not have any of these search terms. However, you know for a fact that document 1 is very much related to this search query. Die, dagger, all these are related to this. Of course, D5, I agree that it's completely irrelevant. Yep, this is completely irrelevant. But then when you look at D1, that's to a great extent relevant. Okay, so your regular search, your regular thought process is unable to help you solve this. Number 1, remember that. Number 2, we are going to take this unstructured data and bring it to a structured format. And this structured format is term document matrix. You take all the terms which are available and list down here, and then you have 5 documents, those will be listed down here. In document 1, you have Romeo and Juliet. So you put a 1 against Romeo, 1 against Juliet, rest all will be zeros. Then if you look at document 2, you have Juliet, happy, dagger. Juliet, happy, dagger, rest all are zeros. Then you have Romeo, dagger, die also. So Romeo against Romeo, you put a 1. Against die, you put a 1. Against dagger, you put a 1. Rest all zeros. In that way, you populate for document 4 and document 5 also. But when you formulate in this way, there will be a lot of zeros. Whenever you have a lot of zeros, it is called as sparse matrix. It is called as sparse matrix. All right. What should I do now? We will try to use the same table in our and then see how to proceed further with LSA. Because once you have this term document matrix, all that means is you could just get this component. You got only this component. Now we need to decompose this into U sigma V transpose. To do this U sigma V transpose, we cannot do it manually using hand. We will make use of programming language. Our Python can be used. So first, let me go here, and we are going to first discuss about basic matrix operations. Okay. If you do simply help of a matrix, you get to see everything about the matrix. Okay, so here I'm saying I want a matrix which has these two numbers. I want to represent these as a single row and two columns. And I want to arrange these by row. I'll run this. So when I say show me A, it says, okay, 1, comma 2. It has one row and two columns. When you do transpose of A, you get one row and two columns. Then you have values 1, 2, 3, 4. You want to arrange them in two rows and two columns. By row equal to true. Oh, then you have B. 1, 2, 3, 4. Transpose of that is 1, 3, 2. When you transpose, you know for a fact that rows becomes columns. Rows becomes columns. Then you have this wherein you're taking a matrix of 1, 2, 3, 4, 5, 6. Number of rows is 3. Number of columns is 2. Okay, you want to arrange them by row equal to true. There we go. We have a C. Now if I say transpose of C, you get the transpose. Now if I take a matrix and have the data points arranged in 3 rows and 2 columns, you get an A. And then if you have 8 numbers, if you want to arrange them in 2 rows and 4 columns, there we go. Then you can do a matrix multiplication. A multiplied by B is C. There we go. You can do this. Then you can take transpose of B multiplied by transpose of A. All these are the matrix multiplications. Then we have identity matrix. You can just do help of diagonal and then you get to see. When you just say diagonal of 5, and if you're assigning that to an object called A, there we go. So when you do this, you have 1, 2, 3, 4, 5 numbers. And then you have A. You're assigning it to an object called A. When you say A, you get all these numbers. Then you can look at inverse of a matrix. So you take a matrix, you take all these numbers, arrange these numbers in 3 rows and 3 columns, and take values and place them in rows, not in columns. Okay, you place them in rows, not in columns. So I'm going to assign that to an object called A. And if you see A, there we go. So you took these values, arrange them by row 1, 2, 3, 4, 5, 6, 9, 1, 2. Then when you say solve of A and assign it to B, and when you look at B here, you get a matrix which is inverse of A. When you use solve, that's the function which is used to get the inverse. And then you can do B multiplied by A, and then what should you get? A matrix multiplied by the inverse of it should give you an identity matrix. Oops. Why is it not giving me in that way? Yeah, it's giving. Right. So these are not rounded off. These are in decimals. This is nothing but 1 only. 111. This can be written as minus 5.551115. Whenever you have e, it is 10 minus 17 raised to the power minus 17. This will be minus 0.1, 2, 3, 4, 5, 6. All those 16 zeros and 5, 5, 5, 1, 1, 1, 5. It's approximately 0. So you have all zeros here, and here you have a diagonal matrix which is having all 1. Okay, and then this is the orthogonal matrix that I've written. So the same thing I'm taking. I'm arranging these values in 3 rows and 3 columns, and I'm arranging them by rows. You have A, all these numbers 2 by 3, minus 2 by 3, 1 by 3. In this way, 2 by 3, minus 2 by 3, 1 by 3. The next 3 would be 1 by 3, 2 by 3, 2 by 3. Then the next 3 would be 2 by 3, 1 by 3, and minus 2 by 3. So 3 rows and 3 columns. By row is equal to true. So you have this data. And what is a property? If you multiply any 2 columns, okay, if you multiply any 2 columns, that is, you take this matrix A, all the rows come up first column. So that means just the first column. If you multiply it with all the rows of the second column, all these 3 rows of the second column, when you multiply these two and when you add them, when you do a sum product, what do you get? 0. Same way when you multiply any 2 columns, you get 0. When you square each and every value and when you add them up, you get 1. And when you solve the matrix, you get the inverse. Okay. All these are the properties that we have seen. That's it, nothing much. So A transpose multiplied by A is equal to identity matrix. This is also something that we have discussed. So when I multiply these two, give an identity matrix. Finally, the eigenvalues, the same matrix example that I've given you, 2, 0, 0, 0.5. You have all these 4 numbers, 0, 2, 0, 0, 0.5. You want to arrange in 2 rows and 2 columns. And you're creating a matrix and assigning it to A. And here we have A. Then you're saying eigenvalue of A, and you're assigning it to this object. These are the eigenvalues or eigenvectors that you get, and here are the eigenvalues. I mean, there are multiple solutions, obviously, right? 2 could be an eigenvalue, or 0.5 could also be an eigenvalue. Minus 1, 0 can be an eigenvector. 0 minus 1 also can be another eigenvector. Okay, that is what it means. You can try out the same thing which we have done. Watch the recorded video if need be. You'll understand. Eigenvalues, eigenvectors. I'm just saying that, my dear friends, there are basic matrix operations which one should be aware of. Why? Because when I now explain you SVD, you'll understand it better because you already have the basics. Why SVD? Hey, because we are learning about topic modeling and we are discussing about LSA, which is also called as LSI. Why are we using this? To extract meaningful insights from your textual data. Extract insights. okay, for this purpose. Now, I'm creating a matrix of all these numbers. I'm going to say by row, no. When you say by row equal to false, it is going to arrange the data in columns. Okay, and I don't want to show you that part. I will show you this part. Okay, here, this part. Okay, why am I not wanting to show you this? Because this is, or if you feel that you want to see this, I need to go here. So these values, okay, I'm taking all these numbers just to show you that when we decompose, you get U sigma V transpose. Just to show you that I've taken all these numbers. When you say by row equal to false, you don't want to arrange these numbers by rows. You want to arrange these numbers by columns. That is what it means. So let me run it. And let me show you this. So what happens is you take all these numbers, arrange them how? By row is false. So you have to arrange it as a column. Then you have 0, 0, 0, 4. Then you have 0, 3, 0, 0. Then you have all zeros here. Then you have 2 and all zeros. You arrange them in 4 rows and 5 columns. 1, 2, 3, 4, 5. That's it. Now, if you do a singular value decomposition, it is very, very simple. You just say SVD of this. Mathematically, it will do the calculation and give you the output. So you have stored the results of this SVD in this SVD object. SVD$U would give you a matrix 0, 0, 0, 1, 0, 1, 0, 0, 1, all these things, right? When you look at this matrix, that is exactly what is given here. That is exactly what is given here. Okay, and then diagonal matrix, you need to get 4, 3, 2.24 and 0. Let's see. When I say $D, D is your diagonal. See 4, 3, 2.23 and 0. 2.23, and if you 2.236, if you round it off, it becomes 2.24. Okay, and then you also have V, but then this V, you need to take a transpose of that because it's V transpose. When you just say transpose of that, then you get a matrix. This is exactly similar to the matrix that you have here. This is the same as this. Okay, 0, 0. This can be rounded off to 0.45, and then this can be rounded off to 0.89. Same matrix. That's it. And now, if I multiply this U sigma V transpose, if I multiply U sigma V transpose, you need to get back your original matrix. Would I get back? Let's see. We are going to multiply these and X, the original matrix. Let's compare and see. 1, 1, 0, 0. Wow, it's the same thing. So when you take your original matrix, when you say U sigma V transpose, if you multiply this, you're going to reconstruct back your matrix. Okay, now let us not break the flow. Let us complete this. So you also understand SVD. Now, how do I apply these concepts in extracting meaningful insights from your textual data using a technique called as LSA? For this, I'm saying that, say you have data like this and you want to extract meaningful insights from that. So I'm explaining you something called as Google search index in some sense, wherein if a query is given in this way, what documents will get retrieved? For that, you first got this term document matrix. And these matrix values that you have here are the values that are created here. All these numbers that you're seeing. By row equal to true, and arrange the data in 8 rows and 3 columns. Okay, let's see how it is appearing here. I'll have to reduce it a bit. Yeah. Let's see. You want 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And 5 columns. 1, 2, 3, 4, 5. Wonderful. You can. Yep. So it's the same. Let's run it. You have it. Then, if you look at this matrix A, oh, it doesn't have the terms and documents. So I'm going to take D1, D2, D3, D4, D5 and assign it to column names of A. And then we are taking all these rows 1, 2, 3, 4, 5, 6, 7, 8, and then we are assigning it to row numbers of A. And here we go. We have the terms and we have the documents. And then when you do SVD of this term document matrix, okay, you get U, sigma, and V transpose. You get U, sigma, which is diagonal matrix, and then you have V. Transpose of V can be taken. So you're saying SVD of this object $U, so that has the matrix U, and then you're taking the diagonal of this SVD object $D, which will give you the diagonal values. There we go, diagonal values. Now, when you take these two and when you multiply those two, you get you'd actually get something called as terms, but then okay, hold on, I'll get to that. So you're taking V from this, you're taking V, storing it in V, and then taking a transpose. Why are you taking a transpose of that? Because it's U sigma V transpose. Only then you get back your original image or original data. Okay, wonderful. So now you have U, S is sigma V transpose. So you have U sigma V transpose. Sigma is given as S here. This is transpose of V. It's written in that way. Transpose of V. Just the notations. I'm just trying to ensure that the notations are the same. Or notations are given in parallel here. Okay. Now, you take U. You take all the rows and columns 1, 2. Take all the rows and columns 1 and 2. You take all the rows, columns 1 and 2, assign it to this U2. Take all the rows, columns 1 and 2. Okay, then you take the first two. Why am I taking only 2? Because I'm doing a rank 2 approximation. You know about that, right? You know that when you have an image, you can do a rank 1 approximation, rank 10 approximation, rank 20 approximation, so on and so forth. Okay, and it's just that we are trying out rank 2 approximation. You can try out with rank 1 also, doesn't matter. I mean, you have to experiment basically. If I do rank 2 approximation, I'm able to compress the data significantly. Okay, that's the logic. And I'm going to S, which is here. Where is S? Here it is. And I'm taking rows 1 and 2, columns 1 and 2. So you're going here as we are taking rows 1 and 2, columns 1 and 2. Then you're taking a V transpose. You're taking all the rows and columns 1 and 2 of this part, V transpose. You're saying you want all the rows of columns 1 and 2. Okay. And you're taking a transpose of that basically, right? So take a transpose of that. There we go. Because you're transposing it. Now, all this is fine, wonderful. But then our end objective is simple. We want to get to this LSA, which will help us extract meaningful insights. Yeah. So you had X, you decompose that into U sigma V transpose. Now what we are going to do is we are going to multiply U and sigma. The moment you multiply U and sigma is in some sense going to capture the terms, information of the terms. Let's see how that would capture. So if I take just U and sigma, when I multiply, I'm taking a rank 2 approximation. I'm not taking the complete matrix. Okay. And when I multiply these two, you get something called as terms. Why didn't I run this? So how many terms did you have? 8 terms? 8 terms. So do you have 8 here? 1, 2, 3, 4, 8. Wonderful. So these 8 rows are in some sense capturing the information of these terms. Once you're done with this, the next thing that you have to do is you have to create query. What do you mean by query? Okay. What was a query that we have used here? We have used a query which was this thing, yeah? Yeah. Dice and dagger. Dagger is a 4th term here. Die is a 6th term. Okay. What did I say? When I multiplied this X equal to U sigma V transpose, which can be written as US V transpose also. So when you multiply these two, this is rank 2 approximation that you have taken. And when you multiply these two, you get terms. It captures information of terms. You have 8 terms and then you have 8 rows. Dagger is this 4th one and die is 6th. So all you do is you take these two and take an average of these two. Okay. And then take these two and take average of these two. What do you mean by average? Simple. You take term 4, row number 4, both the columns, plus add row number 6 terms, go to row number 6, comma, blank space means all the columns, both the columns. And you divide it by 2. When you do this, you'll get an average. You'll get an average, and that average is the query. That average is a query that you're seeing here. So for die and dagger, you got this query. You're representing this as a vector. Why? Because all these terms are also represented as a vector. So you're representing this also as a vector. The next thing that you have to do is just clear this off. Okay. You have to also capture the documents. How do you capture documents? In this x is equal to u sigma v transpose, or we have given a notation like s, right, instead of s, instead of sigma. When you multiply these two, you capture the information of terms, and when you multiply these two, which is s and v transpose, you'll be able to capture, in some sense, documents. Here you capture terms, here you capture documents. Okay, so where we have here, right? When I multiply s into this, it captures the documents. This captures the information of documents. How many documents did we have? 5. How many do we have here? 5. Why only 2? Because it's a rank 2 approximation, hence we have 2. So one is capturing terms, another is capturing documents, and then we have also formed the query. Now, given the query, which document should I retrieve? Given this query, which document should I retrieve? That's a problem that we are trying to solve. To solve that, okay, we are going to use cosine based similarity, which is something which we have already discussed. Cosine based similarity is something that we have already discussed, which is a into b divided by a modulus into b modulus. That's it. That is exactly what we are going to do now. So what we will do is take all the documents, all the 6 documents, or how many ever documents we have. How many do we have? Let's see. 1, 2, 3, 4, 5. Take all the 5 documents, one after another, multiply it with q. Okay, and this is capturing the documents. This SV transpose into q, which is a query, divided by di modulus into q modulus. Simple. So take the first document, take this query, multiply those two. This into this plus this into this would give you a value divided by di modulus and q modulus. Di is d1 first, d1. Right? You have to do this for each and every document. Document 1, this is d1. This is going to be d2. This is d3, d4, and d5. Okay. First do it with d1. So d1 into q. So this is d1 into q. Multiply those divided by, square these and take a square root into square this plus square of this, take a square root of that. This is what we have already discussed as part of cosine based similarity. If you look at this. Okay, we have taken a 1 by 2, right? That's nothing but square root of this. Square root of this. Okay. So I'm creating a matrix with 5 rows and 1 column, an empty object is what I've created. Now I want to populate within this all the cosine based similarities between the query and the document. So for all the five documents, you're saying take the summation of these two, multiply these two, do the summation of all the values, okay, divided by, what do you mean by summation here? You take this multiplied by this plus, so hence summation, this multiplied by this. For I equal to 1, that happens. Divided by square root of, multiply these two, document this and this, you'll get d square, and then take a square root of that, into, take the query term, multiply that, you'll get a square, then take a square root of that. Okay, keep doing it for all the various documents with the query. If you do that, you get something called as ranks. And when you look at this rank, here, document 3 has the highest rank. Of course, when you're searching using die dagger, document 3 would come up because it has die dagger. That is what we have looked at. But the next document which is going to be retrieved is the first document, Romeo and Juliet. So this is called as latent semantic analysis. Latent means hidden patterns, something which we cannot analyze. I mean, this is a toy example, so for explanation, this is how it is. But in real world, you'll have a lot of such documents, and retrieving such documents when you do a Google search or when you are analyzing the documents that you have, be it legal documents or historical documents or life sciences, healthcare, your prescriptions, whatever be it. Okay, drawing these kind of hidden insights would be huge task. Hence, we resort to a technique called as topic modeling, which is LSA or LSI. With this, what's the time? Oh, we are on track. Then let me erase these and let me have this flow made available to you so that you understand. And let me write this. First thing is we create a document term matrix. Second step is we have performed SVD. Then the third thing is we did rank 2 approximation. Then the fourth step was we have used U and sigma, multiplied those. Using this, we got the terms. Fifth, we using sigma and V transpose, using these two, we got documents. Then we created the query term Q. Then finally, we calculated cosine based similarity, which is di into Q divided by di modulus into Q modulus. Wonderful. Yep. And then we got this. From this, you do your extracting of the insights. You extract those documents which are very relevant. I will let this screen remain as is, and we are going to also take quick 10 minutes break now, and we are going to come back by 9:20. At 9:20 we will come back. Until then it's break time. Take a break. Yep. And then come back for further learning. So let me look at your questions. Uh, Oops, there are a lot of questions posted. Where can I get the Python code on my LMS? Okay. Roshan, you have to go to aispry.com. Okay. Go to trainers, my course, whichever course you're assigned to, say you're assigned this program. And when you click on any of those, you see the code, Python code, R code, and the dataset. Okay. Hope that answers your question. Please provide LMS link. Yeah, if you are a participant, you would have been given already LMS access. Supriya, how did you define the direction? Means other than, oh, X and Y axis, that's it, X, Y. When you have this kind of a representation, if you remember the graph book, okay, these books, if you remember, right from your school days, okay, how do you plot 1 comma 2, 2 comma 3, etc.? You will take a basically like this. You term this as 0, 0, 1, 2 in that way, right? Same thing. Same thing. So I hope that answers your question. Um, but then any two value vectors would be an eigenvector only when the vector has three values. It has. I didn't understand Ashish your question. Why are we using R? Sorry, missed the starting. Okay. Um, line to query can. Yep. I think Google search yes uses Ranganath. Absolutely right. However, create rules. Okay. Taking average of a query, one value is only come from how. Okay, fine. See that. I mean, you have to watch the recorded video again. Looking at the document list, how we create the row. Again, look at the recorded video, please. And it will be useful if DTM for that document matrix code is shown instead of just taking matrix values, I think. Maybe. Yes. But then that's already discussed, right? As part of our text mining. And what if we have larger variance SVD works in this scenario? Yes, it might work. Okay, let's move on and discuss more. Where are we here? Yep. So discussed about LSA, latent semantic analysis, which is also known as LSI. Okay, that is what we have discussed. Now we need to switch the gears and we are going to discuss about LDA, latent directly allocation. When it comes to LDA, we use this because usually when you use LSA, it is prone to overfitting. It is prone to overfitting. It overfits. After you have trained your model, and when you add new and new documents, your model starts overfitting. And another reason is when it comes to accuracy, LDA is much better than your LSA. These are the two reasons why people prefer LDA over LSA. Okay, now LDA is called as generative statistical model. Statistical model. It discovers the unobserved groups based on similarity. By looking at the document, you might not be able to make out what logical groups are formed. But LDA will look at that unobserved groups, and it's going to group them based on similarity. Okay. It applies to items or rows or documents that are each made up of different parts. If you look at a specific document, you'll have different sentences, different parts. In some way, by using statistical modeling technique, it is going to figure out which of those words are similar within a document. Okay, in topic modeling, groups are unobserved. Okay, so groups are unobserved. You don't know what groups are formed. Okay, what we can only observe within documents is only words. You take a document, you take all the document, can be one entire document, or each line can also mean a document, each sentence or each paragraph also can be mean a document. Okay, so you take each document, take the words in those documents, and see how are those documents correlated. For example, if you just look at you know cat related documents, some document is written based on cats, what kind of words do you think would appear? Kitten, then what else? Come on, what else do you see? Maybe milk. And what are the other words which you might see? You might see kitty, and you might see uh, purr, and then you might see meow, kind of words. And there are many other words which are possible when it comes to pet, domestic, maybe rat also, who knows? So all these are the words which are related. So these are the kind of words which will have high probability when it comes to cat related documents. On similar lines, if you have dog related documents, what do you see? Barking, dog barks. Okay, and what else? Maybe pet once again, right? Maybe it eats a lot of bones, right? Maybe tail, so on and so forth. So there is a high probability of finding these kind of words in dog related documents. This high probability of finding these kind of words is called as prior probability. Okay, and LDA is a way of measuring the statistical patterns of words within the documents. If you can identify a statistical pattern of what kind of words appear within a document, from that you can actually deduce the topics. And the goal of LDA is to extract the meaningful topics using statistical analysis. It simply uses count of data, count of how many times a specific word appeared, so on and so forth, to extract latent topics. Latent means hidden topics. Latent in pure English, it's called as hidden. So there are a lot of alternative names. Composites means documents. Document could be once again a simple movie review or a product review on Amazon. It could be anything. Then you have parts. Parts are also called as words, and groups are called as topics. These are the alternate names for documents, words, and topics when it comes to LDA. Okay. And then I can give you an example here. Say you take speech a few years back. I mean, you'll do it in R as well. When you have Narendra Modi's speech, in this speech, Modi might be referring to the word toilet because a lot of Swachh Bharat initiatives were taken up, building toilets for the poor and about good governance. Modi spoke a lot about these things, right? So say these are the words that you have and these are the documents. Documents could be paragraph or, it could be 4 different interviews which Modi has given in that way also. And what terms have been used, how many times they have been used in each of the speeches. Say the word toilet has been referred to 10 times in document 1. It is also being referred to 10 times in document 4. And if you look at in 2 and 3, it was never referred to. And if you look at document 4, it contains all these words. Okay. So you're just looking at co-occurrence of words in different documents. How are the words occurrence, or I can say simply occurrence of words in different documents. And LDA maintains 2 probability tables. To extract what? To extract topics from your documents, LDA will calculate 2 probability tables. And you have to logically, as a data scientist, you have to tell to your model that, hey, I want to extract 3 main topics from the document. Of course, again, by refining it further, you'll figure out, but then majorly it's 3, right? And then you have 2 probability tables. One is words versus topics. And you have probabilities which are reflected in this. How likely is it to get a particular word if you sampled from each topic? For example, if you take topic 3 and if you want to sample a word, there is high probability that the word toilet would be picked up. Okay, this is one table which is maintained, words versus topics. And then the next thing is documents versus topics. You had 4 documents and the words which have been used, toilet, poor, and governance. So you have documents versus topics here. And when you look at document 4, there is equal chance of getting any of these topics. And in each of those topics, once again, you have the words. Now, LDA is all about coming up with these 2 probability tables in order to extract the meaningful topics from the data. So it maintains 2 probability tables. These 2, one is words versus topics, and another is documents versus topics. Why? Because at the end of the day, you want to extract, given the document, meaningful topics. And LDA is based on a concept. These are all probability values which are existing. And you have multiple probability values. On one place you have for the different documents, different topics, different words. This kind of multivariate distribution, this is multivariate data. It doesn't have only two columns or two variables. It has words, topics, documents, and topics. It's multivariate, not two, not by, multi, right? Words, topics, documents, multi are being used. So it is called as multivariate distribution. Okay. So, I mean, latent directly allocation depends on something called as directly distribution, probability distribution. This directly probability distribution is also called as multivariate distribution because it describes the distribution of multiple variables of different topics based on different words and different documents. Okay, in that way. So this is a simple high level explanation about LDA. Tomorrow, I think tomorrow or day after, you'll be doing this. And on the same webinar link, if I'm not mistaken, on the same link, on Saturday and Sunday from 7 a.m. to 9 a.m. on both days, you'll have the hands-on session using Python. And at that point of time, you will understand certain things in an even better manner. Okay. Next, let us also discuss about text summarization. What is this text summarization? It is a process of producing concise version of text by retaining all the important information. GenSim, NLTK are the frameworks which are used, and the advantages are that it can help you with respect to sampling. Automatically, your entire document. Okay, I keep saying this that there were days when I was fairly free and I had ample time to read 3 magazines. Trust me, I used to read these 3 every week. Time, Economist, and India Today. And you know what? All these, apart from the daily newspapers, channels, and all that, those were the days when I was extremely free. Maybe, I mean, now if I just reflect upon this, who has the time to read all? I mean, at least I do not have. I'm unable to manage the time, maybe, but then I don't have time to read all these. However, can someone actually take these, you know, uh, magazines or articles, and then can someone help me in terms of giving me a gist of the entire article or entire magazine for each and every article quickly in 4 sentences each? Can someone give me? That's called as sampling without losing the important information. That's text summarization. And Google has this smart reply, right? When you start sending emails, Google is going to automatically fill, or it's going to recommend a few things. It's based on this. Then you have searching. Summarizing the data, text summarization will help the search become faster. Instead of searching the entire document, it would just quickly scan for the important words and do it. This is how things work on your search engine, etc. Indexing is yet another thing. Summarization can be used to create indexes. indexes of your key points. It also helps reduce huge amount of storage which is required because you can only keep the index. It reduces the reading time significantly, especially when you're dealing with legal system. When it comes to legal system, there'll be too many documents which your judiciary judges have to understand. And one of our trainer by name Abhinav has actually worked on this project alongside our team of data scientists, our junior trainers and junior data scientists, along with uh, a few of our past participants. They worked on this, right? On basically how to visualize the data, how to visualize and represent these multiple documents in a visually representable format. Look at, think about a chatbot, right? On our learning management system, we have just started off. We completed for I think 6 modules this chatbot, wherein we are doing this text summarization, so that when you guys have any doubts, when you post a question, we don't want this to query the entire. So what happens is, this is a video has a speech, so you extract only the speech part. Speech can be converted to a text. Once you have this text data, you do an NLP on that, right? And then when you do text summarization, if someone is asking a question on the chatbot on what is LDA, rather than going and looking at this entire text to extract the meaningful sentence, you can keep a summary of it, a summarization, so that when questions are asked quickly, only a gist can be given as opposed to the entire sentence. Yeah, that is exactly what we are doing. Okay. And then we have this text summarization. What is text summarization? Let's see. Text summarization could be from domain perspective, meaning if you're working in the space of life sciences healthcare, and do you know what, we have done this for a Malaysian client wherein we built an AI driven chatbot for their junior doctors, physicians. These junior doctors are usually placed in remotest of the areas where internet penetration is not great. Okay, so if the junior doctor has to quickly refer to internet to figure out what's going on, that might not be feasible. So what we have done is we have built an AI driven chatbot which should work even if there is no internet. That means the amount of data from which your chatbot is going to retrieve shouldn't be very large. So we have done a summarization of SNOMED datasets, and a lot of CPGs, clinical practice guidelines, so on and so forth. That's one simple application. Well, not simple. That's one of the amazing applications, basically. Or your text summarization might not always be domain specific. It could be generic in nature. And whenever you have generic in nature stuff, you can simply use GenSim library of Python, and it does the trick. You also have something called as query based, which we have seen. LSA was query based example, right? Dice, dagger, you searched and then it searched the entire document and it retrieved. So when someone searches in a search bar, or when someone searches in a chatbot, quickly you can get the data. You might have terms and conditions. Do you know what, in Deloitte there was a team called as contract management. Contracts are pages long. As a director, if I were to quickly get a gist of it, and if you throw me this contract, I mean, will I actually have the time to read that? I would rather say, hey, don't you guys have a chatbot which can, probably I'll just type in here penalty criteria, or if there is any SLA. and then it will throw me by extracting that exact information. And then it will spill out the results. Amazing. And then you need not always have a single document to analyze. You need not have a single article, a single email, etc. Right? Sometimes you might have multiple documents, especially when you deal with law firms or forensic analytics. When you even work with forensic, a lot of data should be extracted from web, from their emails, so on and so forth. And the output could be abstractive or extractive. Abstractive means you have sequence to sequence models. That means an input text can be considered as a sequence of input words or characters, while if that's the input, output could be simply put a sequence of words. So input could be words or characters, output could be sequence. This is called a sequence to sequence problem, where we can translate one sequence to another, from one language to another, or from questions to answers. All these are examples of sequence to sequence. Also, you have something called as encoder decoder. Encoder takes input word sequence and you pass it on to encoder, and encoder is going to produce an internal representation. So this is how it would be. You'll have an input, you'll have an encoder and an output. This is basically a kind of neural network algorithm. There is something called as auto encoders, wherein you take your input data, and this is like your hidden layer, and then every neuron will be connected to every other neuron, and you reconstruct this back. And we use this condensed representation, and that's called as text summarization. It can be used in this scenario also. Maybe people who are not aware of neural network at all might not understand this, but this is called as uh, encoder decoder concept is used in autoencoders, which is an unsupervised deep learning technique. Okay, if you don't understand that, forget it. That's okay. By the way, you can also enroll by coming to our website for AI training. If at all there are people who are attending by just subscribing to our YouTube channel. That's what I say. Okay. Extractive means you're going to summarize the original text and then extract sentences or phrases that best convey the meaning. So how best can you do? By ranking the sentences based on importance. And that is exactly what we have done, right? As part of our programming, which I've shown you, LSA, we have done exactly the same. We ranked each and every document based on importance so that you can extract the meaningful. One way is just rank the word frequency, how frequently the words in the sentence appear, and then rank it accordingly, rank the sentence accordingly, and then extract the sentence out. Okay, then you have sentence similarity. This is a measure of how similar other sentences in a document are to a given sentence. So if this is classic example of query. You give a query and you look at how similar the other sentences are to this sentence. Simple terms, a sentence is used to select the summary. Then you're going to only once again do a text rank algorithm and rank all these most important sentences and give them as a summary to the entire document. Another thing is called as clustering centricity. In this, what happens is sentences in the document are clustered into a group, right? You create clusters of sentences, and those sentences which are very, very central to the cluster would be picked up as a summary of this entire document. Something you first create clusters of different documents and then pick up one which is at the center. How do you do it? Of course you have to wait for the Python practical implementation. This is just a theoretical bit of it. Okay, and then there are many things um, on how do you summarize the data, how do you convert your data into a vector format, then how do you perform sentiment analysis, so on and so forth. But just to give you all a gist on what all we have discussed, do you know what we understood on what is the difference between text mining and NLP? Then we have done a lot of data pre-processing. Then we have done a lot of feature extraction, extracting the important features from the textual data. Then we have performed feature engineering. Then you have built a text classifier on top of that. We have built NLP pipeline as part of Python, right? Then how do we extract the data from web? That was all about web scraping. Okay, then we venture into, okay, or we have the data which is in cleansed format, etc. How do you perform topic modeling? In topic modeling, we majorly have LSA or LSI and LDA. LDA is preferred over LSA, but LSA is still majorly used in search engine optimization, if you know about digital marketing. And then, okay, and then we have vector representation of the data. We have, text summarization. I just had a discussion with the South Asia head of Wheelie book publishers. Okay, they, I mean, during the COVID-19, too many people are reading too many things, and then they want their digital books to be summarized using NLP. Small versions, condensed versions of the books can be given as a complimentary to people who are extremely busy. And then we will perform sentiment analysis. In the due course, to understand this LSA and LDA, etc., the knowledge of matrix operations is imperative because it is used in SVD, because that is in turn used in this, which in turn is used for topic modeling or topic discovery. Okay, so tomorrow in India time, Saturday and Sunday on both days. You'll have the session from 7 a.m. to 9 a.m., 2 hours, and you will have to connect using the same link, or it will also be done YouTube live. Connect to YouTube and join. Okay. For our participants who have access to AI Spry, they will be having learning management system within which they'll be having this code. If you're from a very old batch, then drop an email to maybe it's better you drop an email to Sharath at 360digitmg.com and you'll be given access. Okay. For people who are from very old, from long back, I would have trained as part of a different company, then you always will have access to YouTube. All the code would be available in the recorded video. It's also good for your own practice. You look at that and replicate, type it on your machines. It's a very good way to practice. I strongly recommend that. Even to our own participants, I say don't go to LMS, go to the video and then type it. Don't download the code and then start using it as is, because you'll anyways not learn anything if you do that. All right. Now, questions. Okay, hope I answered that question, Chetan. It'll be there. You just get to this link and watch it. Shake. Also there on the sticky note. I just put it. Okay. Although Digital India is being promoted in most of the government ones, the work is still carried out. How could this be digitized? Yeah, government, we have to get in touch with them. There are some tools which could read scan documents and store the data in digital form. Text summarization. Yes, you can relate it to that. Where should I get today's multiple presentation pages in our code? It'll be there on the learning management system. Supriya, I don't understand. Which batch do you belong to, Supriya? Do you belong to any specific batch? Which batch? Can you just comment? Roshan, which batch do you belong to? Do you belong to any specific batch of 360 Digit MG data science training? If yes, which batch do you belong to? Right? Just take that batch. Yeah, who was your trainer? I didn't quite get you. So you take that particular link and send an email to Sharath at the rate 360digitmg.com. Drop an email. If you are a participants, then we would certainly ensure that it's there on your learning management system. Yep, we would do that. Okay, if you have done it through 360 digit MG, yep, certainly we would help you with that. Okay, drop an email to Sharath at 360digitmg.com. Yeah, any other questions? Then it won't be provided, Supriya. You can watch it on YouTube actually. Okay, in query in first hour, it was die and daggers. The probability was highest for as number two or second as probability, whereas there was no connection. Yes, that's how it is, Arvind. Yeah. Romeo and Juliet right? They are related. That's why it came in that way. Okay, sure. So here you have this Romeo and Juliet. They are related, and Romeo and Juliet are related. That's how it is picking up. It's very relevant, right? It's even if you check your common sense, basically, you will feel that okay, I think this document is related. It's not irrelevant at all by any means, because Romeo died by dagger, Juliet, oh happy dagger. So it's speaking about Romeo and Juliet at the end of the day. There is some continuation, some relationship. That's why it is represented in that way. Okay. All right, friends. Thank you all so much. And for our own participants, attendance will be tracked. Don't worry. And please share our YouTube link details to as many people as possible and ask your friends to subscribe. Okay. This is the only help that we expect from you all. Nothing else. Thank you all. Have a good day.